Welcome, everyone. Hello. Nice to see you. So I know there's a lot of people from different time zones. So, thank you for making the time here. Oh, yes, neuroscience. Yes, I think neuroscience very interesting. And, the Nobel Prize in physics actually were neuroscientists. Biophysics, it's very cool that neuroscience and physics is so integrated and it's such an interdisciplinary field. So I'm glad you're interested because of neuroscience. I'm excited to be here with you all. And thank you for making the time here. And I hope we can learn about physics, computer science, and neuroscience. All of these disciplines are very connected with each other. And if you have seen our email, there's a lot of equations we're gonna get through. And hopefully by the end of the session, you will also understand different aspects of physics, computer science, and neuroscience.
Hi everyone, thank you for joining us today. My name is Arushi and I will be moderating today's session. I'm a graduate student at U of T. Welcome to today's session, the Think Like a Physicist series, and this is session 2 of the biophysics and the biophysics part. Our speaker today is Sapalnach Prongkingshai. Sapalnach is a graduate student at the University of Oxford under the mentorship of Professor Morten Kringelbach. Here he is studying whole brain modeling and the hierarchical organization of the brain. That's it from me. Sapu, you can take it away from here.
Thank you so much, Arishi. Today, Arishi will be moderating the discussion. So thank you for being here as well. Welcome to session 2 of biophysics. And as you might know, we're gonna today tackle, all sorts of disciplines from neuroscience to physics and computer science and a bit of information theory. So let's go. What are we going to learn today? First, we're going to go to the very basics of thermodynamics. So even if you do not have any physics background, we're going to study from the very basics of thermodynamics. We're going to go through this very basic equation, which is the relationship between entropy, heat, energy, and temperature. Then we will go a bit into statistical physics, and we're going to learn something called Boltzmann entropy, and we're going to learn what this equation is about. It's a very famous equation in physics. And then we will go a bit over information theory, which is, a bit more computer science, and we're going to learn about Shannon entropy, and we're going to unpack this equation here. And I want by the end of the session, you will actually understand exactly how this equation came to be. Then we are also gonna study, discover about mutual information, which is gonna use, your previous knowledge of Shannon entropy. And then we are gonna learn how we can quantify asymmetric information flow by using transfer entropy. And we will also go in depth about this into this equation, and we're gonna see this very beautiful equation. You can use very simple mathematics to quantify information flow. We are going to use the concept of transfer entropy to study how the brain acts as a hierarchical organization. And, after knowing what transfer entropy is, this image will also make sense. And lastly, we're going to go over more neuroscience kind of research. So we're going to study about global workspace and how there's a set of brain areas that's at the top of hierarchy and control other brain regions. And transfer entropy, Shannon entropy, all sorts of entropy and neuroscience. And I hope you find this session interesting and hopefully it broadens your perspective a little bit. Let's go back to what exactly is thermodynamics. So in thermodynamics, we have to think of a system. So there's a system, there's a surrounding, that basically anything outside the system, and there's obviously the boundary that demarcates the systems and the surrounding. And to give an example, we have this Coke bottle. So this Coke bottle, let's assume that anything inside, the plastic Coke bottle is a system, and then the boundary is obviously the plastic, and the surrounding is anything outside the Coke bottle. And then we have like different kind of systems. So we have an open system. So let's say we have this container here. You could think this container as a system, but it's an open system because there's an exchange of both energy, which is heat, and matter, like water vapor, between the systems and the surroundings. Then we also have a closed system. In a closed system, let's take this kettle here. There's only an exchange of heat, right? But the water vapor doesn't really go out of this kettle. This is an example of a closed system. So the first question for you is, if us, like human being, is a system, okay? And the boundary is, our skin and stuff like that. And this person is drinking and so on. Do you think we are an open or a closed system? So we're gonna have a poll here. Archie, please launch the poll.
Yeah. Can you see it?
Yeah.
Just like, okay, perfect.
And keep in mind the answer is completely anonymous. So please try to participate. I will not, or no one will actually know what you really answered except you. So try your best.
Okay. 80% answered open system and 20% answered closed system.
Great. This is a bit of a tricky question. We are an open system. I'm glad that a lot of you got it right. And the idea is that, exchange both energy like heat and also matter, which is like, we breathe the air out or we breathe the air in, or, you take drinks or basically, liquid from the surroundings. So we are indeed an open system. Great. Now we have been thinking about systems and surroundings. The system and anything in the surrounding basically makes a universe, right? In other words, the energy of the system plus the energy of the surroundings is basically the total amount of energy that exists in our universe. So E stands for energy. Okay, so just keep that in mind. And now this makes us a very good introduction to the first law of thermodynamics, which is energy can neither be created nor destroyed. I mean, we all have heard about this famous law of conservation of energy, but what does it really mean, right? So, if the energy can neither be created nor destroyed, what are the implications for a universe? So, the implication is that the total amount of energy that exists in the universe remains constant. In other words, the energy of the universe never changes. Let's look at this equation here. So delta, this triangle thing, it basically means like a change of something, right? Because the energy can neither be created nor destroyed, you can say that a change in the energy system plus the change in the energy of the surroundings will always be equal to the total amount of change in energy. Or in other words, it would be equal to the total amount of change in the energy of the universe. But because energy can neither be created nor destroyed, the amount of energy of the total amount of energy in the universe never change. Therefore, delta E universe is always zero, right? Because, the energy never change. It can neither be created nor destroyed. The implication of that is that, let's say put 20 joules of energy from the surroundings into the system. It means because the energy can neither be created nor destroyed, it means that the change or the loss of energy from the surroundings into the systems would be the same. That's essentially what this equation is saying. And the second part of the first law of thermodynamics is that the energy can be converted from one form to another. So let's take, a plant, like leaf. They do photosynthesis. They basically, convert light energy, sunlight, into chemical energy so that they can grow and, produce fruits and flowers and stuff like that. Now we have understood the first law of thermodynamics, but I want you to consider this scenario. Okay? It's not a trick question. It's a pretty easy question. So just use your common sense of of nature. Okay? So consider that there's a hot container and a cold container, and we have a tube connecting the two containers. So knowing what you know about nature, without disturbing the system, right? So just put a tube. You are not putting a fan or you're not putting any, heater or anything. Do you think heat can naturally flow from cold to hot? I think there's a poll here, right? Yeah, that's
Yeah.
great.
Okay. So the results are 40% people say yes and 60% say no.
If you really think about it, if you put hot and cold and you put a tube, normally, air from the hot container would go towards the cold, right? Like if you, let's say, have a room that's really cold and you open the door where the outside is very hot, it's very likely like the hot air is going to come in. Normally, actually, heat would not naturally flow from cold to hot just because the energy transfer would want to transfer from a more energetic place to a less energetic place. Therefore, normally in nature, heat flows from hot to cold. But let's say in some random place in the universe we see this exception where heat naturally flows from cold to hot, which I see some of you have answered. Do you think this violate the first law of thermodynamics? So this is a bit more challenging question, but if you really think about it, what is the first law of thermodynamics? The first law of thermodynamics states that the energy can neither be created nor destroyed. So let's say by chance somehow the heat is transformed from cold to hot. Naturally, do you think the energy is being conserved? That's essentially the question.
There's a question in the chat. Wouldn't the cold be resisting the heat as much as the heat resists the cooling?
So I want you to think of, which we will cover in the later part, but I want you to think of heat as energy. Okay, heat is basically energy. The heat or the energy will always want to flow from a more energetic place to a cold energetic place. Or think of like if you have two containers where the hot container has a lot of balls, which like a lot of particles, and the cold container have very less particles. And if you somehow connect the two, the hot container with very energetic particle would kind of rush to a less crowded place. So think of heat that way. Don't think in terms of like wind or stuff like that. Think of heat in terms of, particles being very energetic and so on. Great.
Yeah, release the answers uh, to the poll. 40% answered yes and 60% answered no, and no was the correct answer.
Yeah, great. Actually, despite we know that the energy would not transfer from the cold to hot naturally, this still does not violate the first law of thermodynamics because because the energy is still being conserved. And to answer that question in the chat, I want to show you a very elegant example explaining why the heat would always transfer from hot to cold. Okay, but just give me like a few moments because we will cover in the second law of thermodynamics. So the first law of thermodynamics just simply states that there's a conservation of energy, but the second law of thermodynamics is basically trying to find the principles of physics that explain why there's a certain direction that nature takes. For instance, why does energy always transfer from a hotter place to a cold place? Or why does energy always transfer from a more energetic place to a lower energetic place? Or if you're familiar with the concept of diffusion, why do particles diffuse from an area with more particles to the area with less particles? So this is where the second law comes in and try to explain the directionality of the process. To understand second law, you need to know what heat is, okay? And the concept of entropy. So let's say this is a container and you put heat to it. When you put energy or heat, the particles become more excited. It moves around the container more quickly. And so with an increase in heat, because the particles are moving like faster, you can think that there's more chaos in this container. The measure of chaos or randomness is what entropy is, right? In other words, when you add heat or energy to the system, the entropy of that system increases, okay? But now you will see that for any natural process, the heat will always increase the entropy of the universe. So let's give an example again. So, like photosynthesis, right? You transfer light energy will be converted to chemical energy, but we know that each of these energy transfer is always inefficient. In other words, heat will always be lost, correct? So let's say you have light energy and you convert to chemical energy, some heat will always be lost. And because some heat is always lost, which this means that any natural process where there's a loss of energy, it would, dissipate heat. And because this heat increases entropy, what that means is any natural process will always increase the entropy of the universe. Okay, now I just said a lot of words, but I will slowly unpack what I said, okay? Just to repeat, what I was trying to say is that in any natural process, the entropy of the universe always increases. And when I mean natural process, I mean any process that does not require, adding more energy. Any natural process. So you let it be. And then because we know the conservation of energy, we know that the change of entropy in the system plus the change of entropy of the surroundings will always equal to the total amount of change of entropy. In other words, the change of entropy in the universe. And this, because we have just somehow established that for any natural process, the entropy of the universe always increases, it means that for any change in entropy that occurs in a natural process, it will always increase the entropy of the universe, or, the entropy of the universe will always increase. So, in other words, this is why most natural process, without adding any extra energy, is irreversible. Again, I know this might not feel intuitive yet, but I want to try and explain what does it really mean for a process to be irreversible, or what does it really mean for the process to be natural, and that will answer that question in the chat as well as to why the heat always transfer from hot to cold. So let's consider this initial setup where we have a hot box, and like it's 7 degrees Celsius, and you have a cold box, and the initial temperature is 10 degrees Celsius. And then you connect the tube. So let's say this is hot air and cold air, and you connect the tube. So you know that naturally there will be a heat transfer from the hot to cold place, right? And as we have established before, the heat will usually not transfer from the cold to hot. After some time, if you like have seen in real life, when you connect a tube between hot and cold room, eventually, without disturbing this natural process, the two rooms or the two containers will become at equilibrium. Where before it was 70 degrees Celsius, now both of the containers become 40 degrees Celsius. So I hope this makes sense as to why the heat always transfers from the hot to cold place. But what do I mean by it being irreversible? The question I want to ask is that, let's say I leave this container for in the next 1 million years, okay? And we don't disturb it. Do you think it would somehow return to their original temperature without adding any extra energy? The idea is that without adding any extra energy, the two containers will remain at 40 degrees Celsius. Another example of irreversibility is that, when you drop a glass of water into the ground, the glass breaks or shatters, right? But without adding any extra energy, the glass will remain shattered, right? It cannot magically come back to the original shape unless, we add energy and, recycle it on something. So this is why any natural process is irreversible. Now we have established the idea that there's irreversibility in a natural process. I want to show you that any natural process would always increase the entropy of the universe. To understand that, we need to exactly understand what heat and temperature is. So heat is basically energy transferred due to a temperature difference, okay? So this is what we refer to heat as. It's an energy, it's energy. Temperature, however, is just a measure of how hot or cold that system is. So, we're saying the weather is hot today, so that's what temperature is. But what we're saying about what is heat, though? Heat is the energy transfer due to temperature difference. So again, I hope you understand the distinction between heat and temperature. And as always, if you have any questions, feel free to type in the chat because I don't know, some of these concepts might be quite complex and I would like to unpack as well as I can. Let's now gain a mathematical intuition on, finding the relationship between entropy, temperature, and heat. Let's say we have this cold container, okay? And in this cold container, these particles have less energy to begin with. And when the particles have less energy to begin with, you can think of like the particles are in an orderly fashion, and so there's less entropy. So this entropy is like a measure of randomness or some sorts of things like that. And then let's say you add a small amount of heat. And then when you add a small amount of heat, this thing becomes significantly hotter, or in other words, it gains significantly more amount of entropy. In other words, adding small amount of heat energy should significantly increase the system's disorder. However, let's say we have an already hot container to begin with, and then you add a small amount of heat. This container, the particles are already very energetic to begin with, and then you add a small amount of heat. Then, after some time, this particle becomes hotter, but it just becomes slightly hotter because it was already hot. And so, in other words, it gained just a bit more entropy despite adding the same, amount of heat or amount of energy to it. In other words, adding the same amount of heat or energy causes a smaller relative increase in entropy or in disorder for a system that already had a high initial temperature to begin with. Now, use that example to gain a mathematical intuition of this equation where a change of entropy equals the amount of heat transfer, so Q is the heat transfer, divided by the temperature of the system. So let's take that very same example, okay? So let's say you're applying a small amount of heat of 100 joules, and the initial temperature of this cold box is 10 degree Kelvin. Kelvin and Celsius are the same, just that they're on a different scale, so it doesn't matter, but it's a temperature unit. Just think of it like that. And let's assume this equation is true for now. We would see that the change of entropy is amount of heat gained by this cold container, so 100 joules, so delta Q, divided by the temperature, which is 10 Kelvin, and you can see 100 divided by 10 gives 10 joules per Kelvin. That's the change of entropy or the amount of entropy gained for the cold system. But let's consider this hot system, right? You add the same amount of heat, So the hot system, it's gaining the same amount of heat, which is 100 joules, but because it already had a higher temperature to begin with, in other words, the change of entropy is 100 divided by 100, which is 1 joules per Kelvin. And as you can see, this is exactly what I have told you before, is that for a cold system or an initially lower temperature, adding a small amount of heat will significantly increase entropy. However, adding the same amount of heat to an already very hot container would cause a small relative increase in the entropy of the hot system. And understanding that equation now will allow us to establish why the entropy of the universe always is greater than zero for any natural process like, heat transfer from hot to cold. We know that a change of entropy in this hot system would be the amount of heat loss to the cold system divided by the temperature of the hot, and the change of entropy in the cold system would be equal to the amount of heat gained from the hot system divided by the initial temperature of the cold system. Let's say that there's 100 joules of heat transfer, okay, for simplicity. And so we would plug in into this Q here. So in other words, 100 joules of heat is lost from the hot system, and 100 joules of heat is gained by the cold system. And then you divide it by the temperature, which the initial temperature. And as we can see, we see that the entropy of the hot system, there's a negative -1, which means it lost 1 joule per Kelvin of entropy. Okay? The entropy of the cold system gained 10 joules per Kelvin, and that is what we have established previously as well. And remember, because of the conservation of energy, the change and entropy is kind of like in some sense, is related to energy, which we will see. But you see that the entropy, because of conservation of energy, the entropy of the hot plus the change of entropy in the cold would be equal to the total change of entropy in the universe. So, which means that the change of entropy in the universe equals -1 because the hot system lost -1 or lost 1 joules per Kelvin, and then plus the entropy gained by the cold system, which is +10. And you can see that somehow the total change of entropy in the universe is positive. So what this means is for any irreversible process like this one, will always increase the entropy of the universe. I hope that's very cool. So to summarize, the entropy, it's kind of like you can use interchangeably as like, a measure of randomness, a measure of disorder. And another important point is that for any irreversible change or any natural process that cause irreversible change, there would be an increase of entropy in the universe. I think there's a good time for a short 1 to 2 minutes break. I'm open to any questions with what we have discussed.
While you guys are preparing your questions, I have one for you, Sapo. Um, have you interacted with physics throughout your academic journey? As I can see that a lot of it seems, is involved in neuroscience.
Yeah, that's a great question. I definitely did physics in grade 9 and grade 10. But in grade 11, grade 12, I could choose two science subjects. So I did biology and chemistry because I was very interested in neuroscience. However, in undergraduate, I felt that physics is kind of very integrated with neuroscience. So I ended up taking like an intro to physics course. But with that said, your knowledge of physics doesn't always have to be confined within what you learned in the course. I think this should show an example of how, even without a formal physics training background, you can understand the principle of physics behind neuroscience. And I know for now you might think, okay, how is this entropy related to neuroscience? But if you stick with me to the end, you will see how some of these concepts become really intuitive and relevant to understand neuroscience. This is a great question. Yes, go ahead, Kajit. Hello, nice to see you.
My question's related to like entropy itself. So, is there any way to reduce the randomness of this system,
Yes,
or
of
is it
course,
just
there's a way to reduce randomness, but you need to add in energy to it. So, for instance, let's take this example. So far, we have only been describing the natural process. Okay? So, in other
Mhm.
words, there's an increase of entropy in the universe. So, let's assume this glass is quite less entropy. It's like in an orderly fashion, right? But let's assume you drop this glass and you see it's chaos now because you just dropped the glass and the potential energy, like from when you drop, is converted to kinetic energy and that shattered the glass and so entropy increase. Now, your question is basically asking how do we convert this shattered glass back to this orderly glass. So that would be an example where you're trying to, make things more in an orderly fashion. So the way you do that is you use more energy, right? So it could be that you somehow gather these glasses together, you process it in an industry where you add heat and you melt it and stuff like that, and then you can make a new glass. So yes, you can always increase or decrease entropy of that system by adding more energy. But so far, what I've been trying to describe is a natural process, right? A process where you are not disturbing any of it. You're just letting the energy transfer from one form to another. That's when it's irreversible and there's nothing you can do about it if you leave it naturally. I hope that makes sense.
It does.
Okay.
Given that there's only a finite amount of like, if there's a fixed amount of energy within the universe, at some point, wouldn't all this energy become entropy?
We are talking about the change of entropy in the universe, right?
Hmm.
So entropy and energy is a bit different. So energy is constant. So the
Yeah.
amount of energy is constant. But the entropy is talking of, you can think of how energy is being arranged in different forms, right? Does that make
Hmm.
sense? So entropy is not really energy. Entropy is just saying like randomness. It's just a measure of randomness within a system. Maybe through other sessions, maybe you will gain a sense of what entropy is, okay? To the next part, maybe it might help. And if not, towards the end of the session, I would try to explain better, okay? Okay, let's stick with me then. Great question, though. Thank you so much. So far we have studied the macroscopic system that relates to entropy. So, temperature, heat, these are the macroscopic system. We are seeing a system as a whole, and then temperature and heat also relates to pressure and volume and so on. So that's great. But the question is, what governs these macroscopic system? The answer is it's the microscopic system that governs these things. What if you add energy to the system, what is really happening is changing how the atoms move or how the particles, move around the place, or it might affect how, the atoms are arranged in different ways. So this is another concept of entropy, which I hope I can clarify Kajit's question through this explanation of microscopic system. Now we're going to dive into statistical mechanics or Boltzmann entropy. And so statistics always relates to probability. And understanding problem is very important when we are considering at a microscopic scale. But to gain an intuition of what Boltzmann entropy really is, I want to show this very simplified example of a statistical mechanics problem, okay? So let's say we have four particles. They're the exact same, but I'm just gonna color code just to give them like an identity. So let's say we have a green, red, blue, and golden brown, and then we have two containers here, a pink and a blue container. And the question is, how many ways are there to arrange four particles into two containers? So it could be like, we can put green and red into one, blue and golden brown into another, and you can swap them. So that's already two ways. So the question is, how many ways are there to arrange four particles in two containers? So this is a statistical mechanics problem. Let's see how many ways we can actually arrange. The way we arrange these things, you can think in terms of macro state and micro state, okay? So for instance, you might be like, oh yeah, you can put four particles into the left container. For now, let's call it a macro state one, where four particles on the left and zero particles on the right. And then, or you can have, let's say, oh no, actually you can do three on the left and one on the right. So that's the second macro state. Similarly, you can do two on the left, two on the right, one on the left, three on the right, or none on the left and four on the right. So you can see there are kind of five different ways we can divide the number of particles in this. So we will call these a macro state. But why is this a macro state and not a micro state? You might ask. The answer is that macro state only tells you the number of particles that will go into each of these containers, but micro state will tell you exactly which particles will go. So for instance, macro state 2, 3, and 1, it doesn't tell you whether, green, red, and blue should go into this one, or is it green, red, and gold and brown should go into this one. So that's the difference between macro state and micro state. To clarify, this is a diagram that shows the difference between micro state and macro state. So let's take a 3, 1 macro state, right? So if you think three particles on the left, it could be done in four different ways. So you can put golden brown on the right and the remaining on the left, green on the right and the remaining on the left, red on the right and the remaining on the left, and so on. So as you can see, for each of the macro state, so for 2 and 2, you have six different ways of doing it. For 1 and 3, you have four different ways of doing it. and 0 and 4. There are only one way to do it because you're putting all of them. So this is what a microstate is. It's basically saying how many ways can you arrange into each compartment. In other words, for this entire system that we are seeing, there are 16 possible number of arrangements, or in other words, there are 16 possible number of microstates that exist. And this is essentially, the question that we asked earlier is that how many ways are there to arrange 4 particles into 2 containers? The answer is there are 16 possible ways. And the number of microstate in a given macrostate or a given system this is the W that the Boltzmann equation is about. So I would read this out. So this is basically saying entropy equals some constant, Boltzmann constant. You don't have to worry about it. Ln W. Ln is just its logarithmic base e. But again, you don't need to, even if you don't understand log or ln, it does not matter for this session. But all you need to know is as you increase number of microstates, there's an increase in entropy. Okay? So if you think intuitively, what this means is that for the macrostate 2 and 2, there are 6 microstate, which is the maximum here. So what this means, this particular macrostate 2 and 2 have the highest entropy, right? Because they have the highest number of microstates. So, this is the picture, the Boltzmann equation that's engraved on his tomb. I thought that was an interesting picture. The reason they do that is it's so influential, the equation. But anyways, so for each macrostate, then, we can use the Boltzmann equation to calculate the entropy for each macrostate. Okay? So if you really think about it, if you put all of the 4 particles in one and 0 in the other, you can think that because there's only one possible microstate, it's the minimum, this macrostate 1 and 5 has the minimum amount of entropy. However, like I've shown before, if you put 2 and 2, there's like more possible number of microstate. This means it has the maximum entropy based on this formula. But what's the implication of this, you may ask? So the Boltzmann equation is very useful to calculate the level of entropy for each macrostate or each configurations. Because the more entropy it is, it would be the most likely macrostate, right? So if you think about it, if you take a macrostate of 2 and 2, because there are 6 possible microstate, it's more likely to be in this form. And that's why you see in nature a lot of things tend to move towards equilibrium. And if you think entropy in terms of chaos or disorder, you can think entropy in terms of spread as well. So this system has more spread of particles, and if you think of it, more energetic particles tend to be more spread. And therefore, this also, aligns with our, notion of entropy in that when there's more spread or more energy in the system, it correlates to more entropy kind of thing. And if you recall as well, the system will always tend to move from a lower entropy to a higher entropy state. So let's say on the left here, you connect the two, right? You connect the 2 containers somehow and you allow it to move naturally. It would actually, common sense in a natural process. The particles will always try to spread and be at a state where there's higher entropy. So in other words, when there's a higher amount of microstate or W, there's a higher spread or disorder or entropy within the system, and the system will always want to move towards a higher entropy state. So this is what the Boltzmann equation is trying to say, but at a microscopic level. So even if you don't have intuition for Boltzmann entropy, that's completely fine. But what I want to tell you, the most important part is that the Boltzmann entropy assumes that we can equally access all of these microstate. In other words, it's saying that at a given chance, let's say for the 3 and 1 macrostate, there's an equally probable chance of the nature showing up with these 4 configurations. In other words, if we to randomly pick this particular macrostate, it's possible that, that blue would be on the blue container and the other 3 would be on this. So in other words, the nature can equally access all of these microstates. But the question is, what if microstates are not necessarily equally probable? In other words, let's assume that somehow in the nature, something happens in the nature in such a way that the blue particle cannot somehow go into the blue box. Let's say there's a rule that says that. And or maybe there's something in nature that makes it very biased to access this particular microstate where, red, blue, and golden brown is together on the left side. That's the idea. The Boltzmann entropy, it cannot calculate, the entropy when each of the microstate is not equally accessible. So what do? We need to somehow model the surprise element or the uncertainty of accessing a certain microstate. And this is where the Gibbs entropy in statistical physics and Shannon entropy in information theory comes in. And Gibbs entropy and Shannon entropy has the exact same formula, except that Gibbs entropy applies to the statistical physics system or a microscopic system, where the Shannon entropy applies to a system where there's uncertainty in like an event or like and information. So we're gonna focus now on Shannon entropy, but before that, I want to summarize what we have learned so far. We have learned that most natural process without adding extra energy is irreversible, and we have understood this equation. And then we also learned about the statistical physics, about Boltzmann entropy, and we have shown how the system always wants to move towards a higher entropy state, or in other words, the system wants to move towards a macroscopic state with highest number of W. Okay, so like we have seen, it always wants to move towards like the 2, 2 rather than the 4, 0. Now we're gonna try and derive Shannon entropy, and this would be, the second part of the session. We will take like a 2-minute break. If you guys have any questions so far.
Okay. I have a question. Supper for you. What kind of math do we need to understand these sort of biophysics principles? And what do you recommend for beginners?
Great question. It depends on where you are at your academic journey. I personally think that to understand some of the biophysics, you need very minimum mathematical background, because I think the idea of biophysics is that you understand conceptually how it works. So I think that's the first stage to begin with. Unless you have like an engineering background, obviously that's great. But a lot of people do want to understand physics, and it's totally fine if you don't have any mathematical background. And as you can see, I hope you understand different sorts of entropy without knowing much about like being strong in mathematics. However, if you really want to get deep into biophysics, I would suggest learning a bit of calculus actually, and also learning, about for statistical physics, you will know we will use a lot of probability and statistics. And then so calculus, statistics, yeah, and actually linear algebra sometimes helps. So and understanding those mathematical equations in like these papers. So to conclude, something about calculus, a bit of probability. Oh, and maybe like the basics logarithm, and like how like simple linear equations and those help too. Great. So we have so far studied Boltzmann entropy, and now we know why we need to study Gibbs entropy is to, measure the uncertainty element. So let's try to derive the Shannon entropy. And now is the very exciting part, because this will be very relevant to neuroscience. And what we have talked about entropy hopefully gives you a sense of what entropy really is. And let's go. So what is Shannon entropy? So Shannon entropy is a measure of uncertainty or information content in the system. What does that mean? Well, let's figure out. But I want to show you that, entropy is this mysterious concept of uncertainty, randomness, disorder, and things like that. They all are saying the same thing, but it's just very beautiful how they use this concept to make it applicable to all sorts of different disciplines. To gain a sense of Shannon entropy, we first need to understand what probability is. So let's say we have a bag of apples. Actually, no, we have this bag and it has like 6 apples, and this bag only contains apples, okay? It doesn't contain any other fruits. The question is, what is the probability or certainty of picking up an apple in a bag filled with apple? You want to launch a poll?
Okay. So 40% think it's 1, and 20% think it's 0.5, 0.25, and 0 each.
Great. So if you really think about it, because this bag contains only apples, the other fruits will not magically appear. Let's assume we're on Earth. And if the bag contains only apple, it's very likely that we're going to pick only apples. So it's quite certain that we're going to pick an apple if the bag is filled with apples. So that's why here it's very certain. But I want to show you this mathematical notations in that to say P, probability of picking an apple, you write P, which stands for probability, and then bracket means of, and apple is apple. So probability of picking up an apple is 1, and 1 stands for, 100% basically, in case that wasn't familiar. Now we know this bag is filled with only apples. What is the probability of picking up an orange? So we have another poll.
So 83% people think it's 0, and 0.7 and 17% think it's 0.75. Yeah.
That's great. I'm glad you guys picked up on that. And because there is no orange, the orange hopefully will not magically appear on Earth. So we know that the probability of picking up an orange would be none. I hope you understand the concept of probability of like 0, 0.25, or 1, and so on. Now I want to show you what is surprise, right? So uncertainty is basically the same thing as surprise. Same scenario, if you have a bag filled with only apples, how surprising would it be if I pick up an apple?
Okay, yeah, 83% answered 0, which is correct.
Cool. So that's awesome. Because this bag only has apples, it would not be a surprise to pick an apple, right? But how surprising would it be if I pick up an orange?
Yeah, so 100% said very surprised.
Yes, so how surprising would it be if I pick an orange? All of you have answered very surprised, and that is correct because, you know, with no orange in the bag, obviously it would be impossible to pick up an orange, therefore you would be very surprised. In other words, as the probability of seeing an outcome increases, like picking up an apple, the surprise level decreases, correct? And as you can see with apple and orange scenario. But now we need to find a mathematical function or a mathematical way to show the relationship between probability and the surprise, right? Like these two are somehow related, but how exactly they're related? So you would think that probability of seeing an outcome is inversely correlated to the surprise. And so you would think that surprise equals 1 by probability, but actually that's not the case. Let's look at this again. So we know that the probability of picking up an apple is, 1, it's very certain. And we also know that surprise of this outcome should be 0. But we know that you can't just divide 1 divided by p of apple give surprise. Like that's not correct because the surprise would still be 1. But the idea is that they have found that using logarithm is actually a very good way to model this. Again, you don't need to understand logarithm per se, but just know that log 1 divided by 1 gives 0. So somehow log is converting probability or the inverse of probability to model surprise, basically. So in other words, surprise of an event x, so this x can be like, pick up an apple, is equal to log 1 by probability of x. So I hope that makes sense. And similarly, for picking up an orange in a backfield with apples, use the same formula, which is log 1 by 0. And log 1 by 0 is same as 1 by 0, which is infinity. And this makes sense because the amount of surprise picking up an orange is infinite because you would be very shocked to see an orange. If you think of surprise of an event, understanding uncertainty or surprise also tells us the certainty or the amount of information within an event. You see, these two are actually the same thing. We will denote surprise or information about an event as I. Remember, the bracket stands for of, right? So here we can read it as information or surprisal of an event x equals log 1 by probability of x. And this 2 here in logarithm, we have like a base or something like that. But you don't have to worry about this, but just know that this formula is for an information theorist, and we often use it for computer science to quantify the amount of information contained in any message you send. And because all of the message you send is in like bits, 1010 and stuff, so using base 2 kind of makes calculation a bit easier. But again, not to worry, just know that this exists just to show that we are working in a system of computer science. More importantly, so far we have calculated surprise of only one event, right? We have only calculated surprise of picking up an apple. Like it's one event. But how to calculate the average surprise of a series of events? So for instance, what is the amount of surprise of picking up picking up apple or orange 1,000 times? So this is where Shannon entropy comes in, and it uses this equation a lot. Let's get into it. So to understand Shannon entropy, I would like you to consider a fair coin toss. I hope this is something everyone is familiar with. But the idea of a fair coin toss is that when you flip a coin, it either land on head or tail. Okay? And in a fair coin toss, we assume there's a 50% chance of getting head and a 50% chance of getting a tail. In other words, the probability of X, which can be head or tail, is 0.5 and 0.5. Now, remember to calculate the surprise for each of the outcome or each of the event, you use this formula of the surprise formula, which is log 1 by probability of X. And if you plug in the values, you will get that the probability of surprise for head is 1, because log 2 base 2 gives 1, and for tail as well, because the probability of getting head or tail is the same. So the amount of surprise for getting either head or tail is also the same. So I hope that makes sense. This table makes sense. Now, let's say we toss the coin 100 times, okay? What are the expected number of head or tails? And obviously, because it's a fair coin toss, we know that out of the 100 times, we will get head around 50% of the time. So we are expecting around 50 heads. And similarly, we're expecting 50 tails. But the question is, how much total surprise do we expect from getting heads in 100 coin flips? In other words, out of 100 coin flips, we have 50 heads. And what is the total amount of surprise for 50 heads? So this is a very simple calculation. So we know that for one head that you flip, the amount of surprise is 1.0. So if there are 50 heads, it means that you do 50 heads times the amount of surprise for one, head outcome. So that means the total surprise we get from getting 50 heads is 50. Similarly, the amount of surprise we get from getting 50 tails, out of the 100 coin flips, it's also 50. And because of this, we know that after 100 coin toss, we get 100, because 50 plus 50 gives 100. And now we have established that a total surprise after 100 coin toss, or a total amount of surprise after 50 heads and 50 tails, is 100. To find an average surprise for one coin toss, you would obviously divide the total surprise divided by the number of coin toss you did, which is 100 divided by 100, which gives 1.0. This kind of makes sense because for each of the coin toss, you cannot predict whether you're gonna get heads or tails, and you know that each prediction is essentially a guess. Therefore, the uncertainty, the Shannon entropy, or the randomness for fair coin toss is 1.0 or maximum, right? So now this is essentially the Shannon entropy for an average or like an average level surprise for a fair coin toss. We have now understood this, hopefully, but the point is, how do we derive the Shannon entropy equation? So let's go back to the calculations we have did previously. This is basically what we have done, but I will recapitulate again just to solidify things. So as we know that we have 100 coin flips, and because there's 50% chance of getting heads, we know that the expected amount of heads you get is 50 heads out of 100 coin flips. And to calculate the total amount of surprise for head, you basically multiply by the surprise for each of the head. So 50 heads times the surprise for one head, and you do the same thing for tails, and you basically get the total amount of surprise of 100 coin flips. And because you want to find the average surprise for each coin flip, which is essentially Shannon entropy, you divided them by the number of coin toss. This is what we have basically discussed for the past minute or two. But now I want to show you that the Shannon entropy does not depend on the number of coin flips. It's independent of them because you can actually cancel all of these out, which leaves us to this very simple equation. So what is this? This is basically saying that Shannon entropy of a coin flip event can be shown by multiplying the probability of, let's say, outcome 1, which is head in this case, times amount of surprise for getting that outcome, which is 1.0. And we have established that. And you can do the same thing for the tails or outcome 2. X1 stands for, event X or event 1 or outcome 1, basically. X is just a way of saying an outcome. So, and how do we get this 1.0 again, or how do we calculate surprise? We use this formula, remember? It's log 1 by probability of X, and it's base 2. But again, doesn't matter. So we will replace this 1 with that equation, and voila, you get the Shannon entropy. This is actually the Shannon entropy equation for an event with two outcomes, right? So again, it does not depend on the number of coin flips. But what happens if there are three outcomes? Let's say you're picking a bag filled with apples, which is outcome 1, oranges, outcome 2, or strawberry, which is outcome 3. And then somehow you know that the probability of getting apple is 10%, of what was the fruit of orange, 30%, and of strawberry, 60%. And then you use that same formula, the log 1 by p of x1 base 2. You calculate the amount of surprise here, and then you multiply, and you get Shannon entropy. Okay? So I want you to look at this generalized form. And you can see that each of these colors or phrases are exactly identical. The only difference is this subscript here, which is basically denoting which outcome we are looking at. And now, you want to condense this equation somehow, and mathematics has a beautiful way of writing a summation. So the way this summation works is that you replace this outcome by I. So now I is the outcome, and I can be either 1, 2, or 3. So x1, x2, x3, right? So you're basically replacing this outcome number with I, okay? And the way this summation works is that, okay, we are gonna replace I with 1. That's the first number we're gonna replace. And then you get this. Then you're going to replace with the next number. So which is it is always an integer. So the next you're going to replace with I equals to 2, and then you're going to get the blue one. And then you're going to replace the third number, so which is I equals to 3, and you're going to get this red equation. And the summation is basically saying that you add all these terms that you have outputted, and you sum them. Okay? So to repeat, you basically sum all the terms starting where you replace I with starting from this bottom number, which is 1, until you reach the number at the top. So in this case, because we only have 3 outcomes, it's number 3. Let's say you can do this until the nth outcome, right? Like let's say you have a dice with 6 faces, so the outcome n might be 6. So you can do the exact same thing, but you can replace n with 6, or you can replace n with thousands if there are thousands of outcomes. And so this is essentially the Shannon entropy. So to repeat, the Shannon entropy is denoted by H. So H is, Shannon entropy. H, or Shannon entropy of X, equals to this formula, and you sum it and from the first outcome until the nth outcome. That's essentially what Shannon entropy is. So there we go. That's Shannon entropy for you. But again, Shannon entropy only measures one event, okay? So it measures coin flip, or it measures if you throw a dice. But what if there are 2 events involved? So for instance, let's say I want to know whether me flipping a coin would influence the outcome of you flipping a coin, or whether me flipping a coin would influence whether you pick an apple on the bag filled with apple and oranges. So what happens if there are 2 events? Can we use Shannon entropy somehow to quantify the relationship between the 2 events? And so in other words, what if there are 2 events, x and y? And you can ask all sorts of different questions, which I will read them out to you here. So for instance, we can ask, can you quantify amount of information shared between x and y? Or does knowing x tell us anything about y? Or does knowing x help us predict y's outcome? Or does knowing x reduce uncertainty of y? Remember, knowing something or knowing the uncertainty of something is basically the same, like essentially the same thing. Or does knowing uncertainty of x reduce uncertainty of y? Or does knowing uncertainty or Shannon entropy of x reduce Shannon entropy or uncertainty of y? Or are there any mutual information shared between x and y? So I have literally told you so many questions you can ask. These questions that I have said, they have some nuances. There are some differences between them, and we're going to go over it right now. So far, we have understood Shannon entropy, which quantifies uncertainty for a certain event, like a coin flip. But now we're going to go over the mathematical definition of mutual information, which is this equation here. And so basically, this is basically reading mutual information of x and y, or the information shared between x and y, equals Shannon entropy of x plus Shannon entropy of y minus Shannon entropy when you take x and y's outcome. For the purpose of time, I will not go over the mathematical derivation of this. However, I want you to give an intuition of what it means to quantify amount of information shared between x and y. So let's take this case where the information shared between x and y is 0, okay? What does that mean? It means that there's zero amount of information shared between X and Y. In other words, event X and event Y are completely independent event. In other words, knowing anything about X does not tell you anything about Y and vice versa. To give a real life example, it's basically saying that me flipping a coin doesn't allow me to predict what the outcome you're gonna get when you flip a coin. Or me flipping a coin doesn't predict whether you're gonna eat, pasta or like other kind of food like pizza or pasta. So you see that is what it means. It's the two events are independent. However, if the mutual information shared between X and Y is 1, which is the maximum here, it means that even X and Y are completely dependent. In other words, knowing one completely determines the other. It could be like knowing that I flip a coin and get heads would allow me to completely predict what the outcome of your coin toss. So that is the example of dependent events, okay? But remember, mutual information only describes information shared between two events. It does not allow us to quantify the relationship of the two events. In other words, mutual information cannot tell us whether knowing X will help us predict Y's outcome, but not vice versa. In other words, mutual information cannot tell you that there's a flow of information from X to Y, or in other words, mutual information assumes symmetry of information flow, right? Because it's just saying that, there are some common stuff between X and Y, but it doesn't tell you any direction of predictability. So this is why we need a different kind of entropy to answer your question. So we have Shannon entropy, which we know is uncertainty for a coin flip or for an event. We also know there's a mutual information that describes the information shared between two events. Now we're gonna go really deep into transfer entropy, which is, it can capture the asymmetric flow of information and directionality, and the transfer entropy is what is gonna be used to quantify hierarchy in the brain as well. So what exactly is transfer entropy? So this part is saying there's a transfer of entropy from X to Y, or in other words, there's a flow of information from event X to event Y. In other words, knowing X past outcomes helps predict Y's current outcome. And remember, predicting something is same as quantifying uncertainty of a certain outcome. So in other words, it's basically saying if knowing X past values reduces Y's current uncertainty, then it means that there's a flow of information from X to Y, or in other words, somehow we can use information about X to predict Y's outcome. Remember, that's the first thing we came up with. So we're here now, and we're gonna go over this equation, which I hope you will gain some intuition for this equation. So let's say we have y, okay? And this y here has tossed the coin 100 times. And, y has already done that, okay? And then we're gonna record the outcomes here, and you have head, tails, tails, and so on. And we record all of the outcomes for 100 tosses. But now we're in the present moment, and Y is like, I'm gonna make new 101st toss. So now he's gonna make the toss of the 101st toss. The question is, we can ask something like, using information from the previous toss of 1 to 100, what is the uncertainty of Y's 101st toss? So to give you a clear sense, I will reframe the question in case this helps better. But before I do that, I want to also reframe how we can think in terms of tosses. So remember we were saying how, the Y has already tossed one, like 100 times, and this is the 101st toss. But we can replace 101 with T. So let's assume the T toss is the current toss. So let T be 101, let's say. And then you can say that the historical outcomes is toss 100, so 101 minus 1, to toss 1, which is toss 101 minus 100, which is 1, right? So with that in mind, we can ask then, what is the uncertainty of Y's current toss or 101st toss given his previous 100 tosses, or given his previous t minus 100 to t minus 1 toss? And we can depict this mathematically using this equation. So here, for instance, I want you to see that in the bracket, they're like on the left side and on the right side of on the left side here, which is divided by this line, and then you have the right side. So let's talk about the left side first. So in this left side here, it's basically saying it's the Shannon entropy that we know. This is trying to quantify the Shannon entropy or the uncertainty of Y's event and specifically of the current toss. So you know T is 101. This line is essentially saying given or using the information of. This part is basically telling us what information are we using to predict uncertainty of the current toss. And you can see this is y t minus 1, which is toss t minus 1, colon is basically 2, t minus 100 toss. In other words, you can read this basically as we are quantifying the uncertainty of the current toss given or using the information of previous toss from t minus 1 to t minus 100. Okay, so I hope this part makes sense. It's mathematic in some sense, it's a language, and you can always translate it to English. And now we have understood this part of the equation. So let's go to this, the right part of the equation. If you recall here, this is essentially very similar to this part, except you're adding a comma here, and you're adding this red part here. So I want you to try and help me derive this. So can anyone tell me what this comma stands for? I'll give it like 30 seconds. So think of like in English, if you write a comma, what does comma do?
I think it's like also that you're also going to check the uncertainty of the current loss for the X event. You're like the comma means that you're going to also check the uncertainty of the current loss of the or current toss of the X event.
Great, that's good. Tanishwaran says connecting ideas, that's correct. So you can think comma as basically and, right? Yeah, comma as and. And then what does this mean? X t minus 1 to t minus 100. Try to translate it as simply as you can in English. Shiret has kind of said it, to be honest, but
Yeah, the X previous tosses.
yeah. Okay, great. So yes, that's correct. This is basically saying is x previous tosses from t minus 1 to t minus 100. So now, can someone tell me in English what this part of the equation is saying?
I would say that the total uncertainty of the current toss based on adding the uncertainty loss of the Y's previous tosses and the X previous tosses.
Yeah, that's great. Yeah, that's great. So we are still looking at a coin flip, by the way. And this is basically saying the uncertainty of Y's 101st toss given Y's previous 100 tosses and X previous 100 tosses. And so now essentially we know both part of the equation. So the question is, what is this saying, right? So here, I want to show you this example to give you a sense of what transfer entropy is really saying. So remember, you have two parts of the equation here. So let's assume that the left side of the equation is greater than the right side of the equation. So what does this really mean? To explain what does this mean, I'm going to try and explain through different words, right? So what this is essentially saying is that if you see two parts of the equation, both are measuring uncertainty of Y's current toss. The only difference is that this right side of the equation is basically saying, oh, if we use both X and Y's information, what's the uncertainty of Y's toss? While on the left side of the equation is basically saying, oh yeah, if you just use the Y's previous outcomes, what's the uncertainty of Y's current toss? In other words, this greater symbol is basically saying that when you now add information about X previous tosses, it's somehow reducing the uncertainty of Y's current toss, right? So, and if you recall that when we say that knowing X past values somehow reduces Y current uncertainty, then it means that there's somehow a flow of information from X to Y because X is somehow allowing us to inform Y. And so, in other words, by simply knowing more about X history, we can predict Y better. Or in other words, by simply knowing more about X's history, we can reduce Y's uncertainty. So, which means there's a flow of information from X to Y. And in other words, if this equation is greater than 0, which is basically this thing, it means that there's a flow of information from X to Y. So there you go. That's transfer entropy for you. We can use that equation to now capture hierarchy in different systems. So to show you how to do this, I want you to think of like consulting company or like any big company in general, like McKinsey or Google or stuff like that. There's gonna be a management or leadership team. So it could be CEO, CFO, chief of staff, managing director, or like things like that. So you would think that people at the top would, they talk so much to each other, and then eventually they try to make a decision. So, there's a lot of flow of information within the group itself. However, what the CEOs are really doing, it basically get reports from their subordinates, right? It could be like a manager or like a junior intern and stuff like that. So everyone is giving information into the leadership team, and the leadership team basically integrate information. It integrates information and then it outputs like to someone who makes a certain decision about the company. One thing to note is that the CEOs or the leadership team, they mostly receive input of information, right? Because, it's rarely like the CEO is going to talk to this junior intern, but the junior intern would send information up the hierarchy. And the only time the CEO would send an outgoing flow of information is when it needs to make like a big decision for a company. So, same thing with the brain. The brain has a kind of like a group of brain areas that is like the leadership team or at the top of hierarchy. And the idea is that a lot of information is flowing into the CEOs of the brain. And if you think of it like, there's like specialized brain area for attention, for memory about the past, sensory processing, emotion, reward, and stuff like that. It all inputs information into this top of the hierarchy brain area, and eventually it makes a certain decision. This is what we call the global workspace hypothesis in the brain. They hypothesize that the global workspace in the brain has certain features. One is that they mostly receive information from other brain areas. Second, they integrate them by mostly talking to each other. And third, the most of the output they do is it dictates the decision that it's gonna perform like in the present or slash the future. Okay. So I want to show you information flow, what's really happening. Because the global workspace mostly receives information, the global workspace or the brain area at the top of the hierarchy would have the highest level of incoming directed flow of information. And it would also have the lowest level of outgoing flow of information because it's mostly receiving information to integrate stuff. Because the idea of the global workspace is that it mostly integrates information, it means that the information flow is mostly densely connected within themselves than to the regions, than to other regions. And you can basically use transfer entropy measures to quantify asymmetric flow of information in the brain. In other words, you can have two brain areas and you can use the transfer entropy equation. This is basically very similar, just that it's using I instead of Shannon entropy, but it's essentially the same. So if you want to show that there's a transfer information from X to Y, you're basically seeing whether can we use the brain activities of X to predict Y's current outcome or Y's future brain activity. And that means there's a flow of information. And the idea is that for each of the brain regions, so like this one, you can calculate the sum of incoming flow of information from like all other brain regions. And similarly, you can calculate the G out or the outgoing flow of information for each of the brain region as well. And you can sum them up. And the idea is that you can create this heat map of the brain, and you can see that these heat maps, so we have two things, G in, a sum of incoming flow of information, and G out, which is a sum or total outgoing flow of information. And you can see the yellow means it's a high value, high information flow. And red means that there's a low information flow, okay? So that's what heat map is saying. We're almost done. So now we're gonna see like two brain areas just to show you how it works. So let's take this visual cortex, which processes basic visual information. And you can see in this diagram here, this is the visual cortex, by the way. It's like all at the back of the brain. So this is the back of the brain. This is at the front. And you can see because for G in is red here, it means that there's a low incoming flow of information flowing into the visual cortex. However, the visual cortex sends out a lot of information to other brain areas, as you can see from the yellow here. And this makes sense because actually visual cortex is not a part of the global workspace, and all it does is, it processes visual information, but if you detect a line or a shape, it really doesn't matter, right? It needs to be integrated with other things like motion detection or memory or attention, and then it basically needs to send output to the global workspace or the CEOs of the brain. Let's take another brain area called posterior cingulate cortex, which is basically this yellow area and this red area. you can see from the diagram that for posterior cingulate cortex, there's high amount of information going into the posterior cortex. However, the posterior cingulate cortex itself does not send out much information. And why? This kind of makes sense if you now know the function of posterior cingulate cortex. Posterior cingulate cortex is involved a lot in self-reflection, self-imagery, internally directed thoughts. And to reflect on something, you need to integrate so many sorts of information all together. To reflect on something, you need to integrate information from hippocampus, which is for autobiographical memory. You need to integrate info from visual cortex, like vision, so you can imagine things, or maybe like motion. You remember the smell of your previous birthday, smell of the cake, or maybe emotions and so on. So you can see posterior cingulate cortex there's a lot of ingoing flow of information. And the way you calculate the global workspace is you make participants lay down in the scanner and do all sorts of tasks: emotion, gambling, language, motor, relational tasks, social. WM stands for working memory, and also just rest. Basically, just open your eyes and think. And for each of these tasks, you basically try to find brain areas that are characteristic of a global workspace. They just name it functional rich club, just like it's just like a club of like leadership team basically. But the idea is that they basically try to find brain areas that is a part of the functional rich club for all of the 8 tasks that they do. And they found a bunch of brain areas that is a part of the global workspace. And you can see the posterior cingulate is actually one of the part of the global workspace. And it kind of makes sense because to do self-reflection, self-imagery, you need to integrate a lot of things from value, attention, memory, sensory processing about the present, attention, and so on. And then that allows you to, think and, direct your future behavior. So today we are concluding the session. We have learned, thermodynamics, macroscopic system, microscopic system. I hope that kind of give you intuition into information theory. You have learned a bit about mutual information. You have learned about transfer entropy, how information is flowing from one place to the other. You have also learned how transfer entropy is used to quantify flow of information. And finally, you have learned about the global workspace. And I want to end by saying that, I would like to encourage everyone to engage in the post-session questions. These are not compulsory. Shortly after the session, I will post the post-session questions on Discord. And for the certificate or the award, the requirement is that you answer at least 2 post-session questions and maybe respond or interact with at least one person. It can be from the previous session as well. We have different kind of questions that is a part of post-session activities. We have like thinking questions. It would be in the general writing practice channel. We have annotated bibliography, and then you have reflection questions as well. And by the way, this session is recorded and will be uploaded on YouTube. For those in the emailing list, I will also email you the link.
There's a question in the chat. If I review the material, YouTube recordings, complete the assignments for past session 1, also the current session, or complete all the sessions and assignments out of order, can I still receive the certificate of completion at that time?
Great question. So yes, as long as you review the materials, including the YouTube recordings, and complete the post-session activities or assignments for all of the sessions, even if it's done out of order, you would be eligible to receive the certificate of completion. But I want to emphasize that we build these sessions and Discord and the post-session activities because, or actually, Clematis would like to foster your learning. That's our core value. Our core value is to foster your learning, growth in research skills, and critical thinking throughout the process. And hopefully, this session give you some intuition of thermodynamics from your high school or undergraduate concepts, and you can appreciate how this is actually being useful in different areas. Thank you so much for your time. So, if you have any more questions, you can always ask in the Discord channel. I will try my best to answer as soon as I see it, or maybe give me a few days, but I will be sure to give feedback, at least for this session. And yeah, thank you so much, everyone, for being in this session. And thank you.
Thank you.
Clematis Research Empowerment Hub. Empowering research for everyone.